right, so now that we have figured out how to calculate our information matrix in general, I want to go over just a few examples just so we can really solidify how to do this in our mind. So first, we're going to go over an example using a one-parameter distribution, and we are going to find the information matrix. So let's say we have a sample of x1, x1, x2, all the way to xn. So that is our sample of data. And we assume that this sample is from a Poisson distribution with parameter lambda. We don't know what lambda is yet, but we will be using, we could use MLE to estimate what lambda is. And so our goal from this is to solve for the information matrix. So we're going to take you through all the steps from figuring out what the log likelihood function is to taking its first and second derivative all the way to finding what the actual matrix value is. So let's start off with calculating the likelihood function. So our likelihood function is given by L of lambda, and that is the multiplication from I equals 1 to n of our probability distribution function, lambda to the xi times e to the negative lambda all over xi factorial. And so we're going to break this up a little bit to make it a little bit easier on us. So let's break up this first part, the denominator. So this whole thing is equal to 1 over multiplication from I equals 1 to n of xi factorial. And then let's work on this part, lambda to the xi in the denominator. We're going to multiply this times lambda to the sum of I equals 1 to n of xi. And then our last part, e to the lambda, there's no xi's in there, so that we're going to multiply this whole thing times e to the negative n lambda. So we have broken up this function into this now. So this is a little bit more easy to manage. So our next step, always when doing MLE, after we find the likelihood function, we want to find the log likelihood function because it's a little bit easier to work on. So our log likelihood function, little l of lambda, is found by taking the natural log of the likelihood function, big L of lambda. So doing this step by step, we're going to be working with this first part here. That would be equal to negative sum of I equals 1 to n ln of xi. Our next part, lambda to the sum of the xi's, that is equal to plus sum of I equals 1 to n xi, this whole quantity times ln of lambda. And then finally, the natural log of this bit here would just be minus n lambda. All right, so now we are going to be working on taking the first and second derivative of this function here, because this is finally our log likelihood function. All right, so the first derivative with respect to lambda of our log likelihood function. Well, let's look through here. So we're taking the first derivative with respect to lambda. So our only terms that actually contain lambda here are the second piece here, and then the third piece. And so this first piece will just turn into 0 because there's no lambdas there, so taking the derivative of that would turn into 0. And then taking the derivative of the second part would just be the sum of I equals 1 to n xi over lambda. And then derivative with respect to lambda of our last piece is just minus n. And so we want to simplify this a little bit, just because having the sum of the xi's in here is just not ideal. And so we want to go back to just a key definition here. So we know that x bar, our sample mean, is equal to 1 over n times the sum of I equals 1 to n of our xi's. So that means that the sum of I equals 1 to n of our xi's is equal to n times x bar. And so we want to go ahead and make that substitution here. So we're going to say that the first derivative with respect to lambda of our log likelihood function is equal to n x bar over lambda minus n. All right, so now we have to go ahead and take our second derivative, because as we remember, we have to have the second derivative of our log likelihood function for our information matrix. So the second derivative with respect to lambda of our log likelihood function, L of lambda, is equal to, well, let's go back to this function here, which is our first derivative with respect to lambda. This second term will just turn into 0 because there's no lambdas there. And then our first term will be equal to negative n x bar all over lambda squared. All right, we're going to move on to the next page. All right, so now that we have found our second derivative with respect to lambda, we can go ahead and actually figure out what our information matrix I of lambda is. So our information matrix, as you remember, is the negative expectation of the second derivative with respect to lambda of our log likelihood function, L of lambda. So we know what this value is in here, so we want to take the negative expectation of negative n x bar all over lambda squared. All right, and so we can multiply this negative through, so this will be equal to the expectation of n x bar over lambda squared. All right, and this whole thing will be equal to n lambda over lambda squared, because as we remember, the expectation of x bar for a Poisson distribution is lambda itself. So that is how we substitute in lambda for this expectation of x bar. And then finally, just to simplify this down, this turns out to be n over lambda. And this, in the end, is our information matrix. So I guess one question that we should have is, now that we have our information matrix, what do we actually do with it? And like I mentioned before, we can use this information matrix as a way to solve for our covariance matrix. So our covariance matrix, the way to solve for a covariance matrix, is simply the inverse of our information matrix. And so it's really simple. For a 1-by-1 matrix, the inverse of a matrix is just the reciprocal. So for our example, I of lambda, the inverse of that would just be the reciprocal of this value up here, so it would be lambda over n. So in the end, this is our variance of this is the variance of our estimator lambda. And so that is the process for how you go from getting your log likelihood function into your information matrix and then finally inverting it to find the covariance matrix.